হ্যাঁ হ্যাঁ জোম্যাটো। Good, good evening everyone. Welcome to the tutorial on analog communication problem solving session. Today we will be doing autocorrelation, energy spectral density, and power spectral density. So let's begin. Okay, so the first question is that the energy spectral density of a signal can be obtained by taking the Fourier transform of A, the power spectral density, B, the signal itself, and C, the autocorrelation function of the signal, and D, the squared signal. So energy spectral density can be obtained by taking the Fourier transform of what what function of the signal. Is it the PSD, the signal itself, the squared signal, or the autocorrelation of the signal? So this relationship is a standard relationship, like it's called the Wiener-Kirchner theorem. According to the Wiener-Kirchner theorem, the ESD is the Fourier transform of the ESD, energy spectral density of a signal, is basically the Fourier transform of the autocorrelation of the signal. So this is the known as the Wiener-Kirchner theorem. So this is a standard result in signal sense systems. So this is the answer. The answer is autocorrelation function. So we will not go into the derivation of this as it is unnecessary. We will just take it as a result. So the answer is C, the autocorrelation function of the signal. Next, the PSD area under the PSD. The area under the PSD. So what does that represent? Does it represent the total energy, the total power, bandwidth, or amplitude? So the area under PSD So PSD means basically the distribution of power in the frequency domain. So here you have frequency and you have some kind of a distribution of power in this frequency domain. So what does this area represent? Area means integrity. So we are, if this is our PSD, so this is our PSD, we are integrating the PSD with respect to the frequency area. So this basically gives the area, and this also gives the total power, because PSD is the power present per unit spectrum, per unit of the spectrum. What is the power present? So when we integrate it over the entire range of the spectrum, what we get is the total power. So the area under the curve of PSD is total power. So the answer is total power, option B. Which of the following is a property of the ESD of a real valued signal? So the signal is real. What is the ESD like of that signal? So ESD is given by the this is our ESD. So the mod square of the envelope of the signal gives you the ESD. So now the answer is for a real value signal. If xt is real, then mod xt square is bound to be positive. This is bound to be positive. Even if it's not real, it is bound to be positive. So mod xt square is always positive. So ESD is always positive. That is one property of ESD. That is granted. But that is not specific to it being real. Next, is it an even function or an odd function? So here mod xt square is clearly an even function. Mod xt square, because mod xt square, if you make it, it is clearly a, if you take the values, it is clearly an function. Similarly, the ESD, which is just the sum of that, the sum of these mod xt squares, it will be an even function. So the ESD at a negative frequency is just equal to the ESD at the positive frequency. So ESD is an even function. So it is positive and it is even. So ESD is a complex function. Wrong, because if xt is real, mod xt square cannot be complex. Even if xt is real, it cannot. Even if xt is complex, it cannot be complex. ESD is always, by definition, ESD is always by definition a real function, because you are taking the magnitude of the signal. If you are taking the magnitude of the signal, even if it's complex, it's bound to be real. So it's bound to be real, bound to be positive. So it cannot be complex, and ESD can take negative values, which is again false. ESD can only take positive values. And we have seen that ESD, as mod xt square is even, the summation of that mod xt square, which gives us ESD, is an even function. Next, how can power spectral density of a non-periodic signal be calculated? Now, power spectral density is by definition a periodic signal. So just by integrating, you will not get the PSD because PSD is defined for a periodic signal. So you cannot have a defined period. So what you do is you take a small range of that signal. You take a not small, rather you take a range of that signal. You truncate that signal within a limit up to say minus, like here it is written, up to minus t by 2 to t by 2, and you observe it in that range and you find the power spectral density in that range. But you cannot find the power spectral density of the entire signal. You have to limit it in time. So and how do you limit it in time? By truncating. So the correct answer is by truncating. So next, ESD of the product of two signals is equal to the product of their individual ESDs. So ESD of product of the two signals, is it equal to the product of the ESDs of the two signals? Let's see. So ESD of product of two signals is this is simply ESD of x1 x2. Now what is ESD of x1 into ESD of x2? It is integration mod x1 t square dt. So we know that integration is not distributive over multiplication. You cannot just distribute the integration like that. So these two are clearly not equal. So ESD of x1 x2 is not equal to ESD of x1 times ESD of x2. Okay, so it is false. Now this is up to this it was true and false and objective questions. Now we have problem. So a problem is this, that a random binary signal which transmits a binary 1 by a non-negative rectangular pulse of width TB/2 and amplitude 1. So when it wants to transmit 1, it gives you a square shape pulse. And how is that pulse? Rather rectangular pulse. So the pulse width is TB/2 and it has an amplitude 1. So it gives you a pulse like this. Okay, when it wants to transmit 1. And when it wants to transmit 0, it just turns off. No pulse. So the digits 1 and 0 are equally likely. So the binary digits, this 1 and this 0, are equally likely to occur. So the autocorrelation of this signal is, you have to find the autocorrelation of this signal. So yeah, take 5 minutes. I'll be back. Take 5 minutes. Then we can start solving this problem. Take a few minutes to think for yourself and try for yourself. After that, we can start with the solution. Yes, so let's start with the solution. So here there is a autocorrelation. So we have to, what we have to do is we have to divide the time into two kinds of duration, ranges or two sets. So here when we want to transmit one binary one, we are transmitting a pulse. That pulse is z of the width tv by 2, and it is amplitude 1. It has amplitude 1, and when it is 0, it is 0. So there is, at any instant, there is a like half probability that these are the signal is 0, and half probability that the signal is in this pulse. So half of the autocorrelation will be from this, and half of the autocorrelation will be from 0. So if this is like say x1, then let's write it clearly. This is x1. Okay, this part, only this pulse. So rxx tau will half come from 0, the autocorrelation of 0, which is 0, and half will come from the autocorrelation of x1. So whatever is the autocorrelation of x1, eventually the autocorrelation of x is just half of that. Now to find this autocorrelation, one part of the signal is you take two copies of the signal. One signal is held constant, another you shift. You shift another signal. Let's draw it with another ink. Another signal you shift. So when you are shifting the another signal between 0 to TB, between 0 to dB, you get this triangular function, and when it is greater than TB, then this autocorrelation you get another triangular function. The detailed derivation of these triangular functions are given in the lecture. So in the lecture, if you follow the autocorrelation function, they will directly derive these autocorrelations for you, so you can just check that. So those will come half and half, and like that, and when it gets multiplied with the probability 0.5, it becomes 1/4 plus 1/8. So the correct answer is C. Please check this. So this will be uploaded. So with the derivation that you have got in the lecture, you cross verify and check whether you are getting C or not. Okay. For the next part, for a deterministic signal with finite energy, which of the following is true about its ESD? So the ESD can be negative for some frequencies. The ESD is always 0 at the origin. The ESD is non-negative and integrable over all frequencies, and the ESD is symmetric about origin. Let's break down these options. So signal xt is a deterministic signal with finite energy, means it is of finite duration. Finite energy means it is of finite duration. either of finite duration of or even if it is infinite, it is converging. It is converging infinite, like a decaying exponential. It is not diverging to infinity. So, in a deterministic signal, which of the following is true for its ESD? Let's take the options one by one. 3 of them will be false, 1 of them will be true. So, let's do that. So, the ESD can be negative. This is false. The ESD under any circumstance for any signal will never be negative. So, it is a very strong condition. So, it can never be negative for some frequencies. The ESD is always 0 at origin. So again, ESD being 0 at origin means there is no DC power, DC energy, however you say. So that is not always true. If there is a constant term in the signal, you will have a ESD at the 0th part also, zero frequency also. So it is not 0 at origin. So always 0 at origin. Can be 0, may not be 0 too. The ESD is non-negative and integrable. So the signal is a deterministic signal with finite energy. Now, ESD is the integration of this signal. So, since it is deterministic with finite energy, it should give a continuous ESD. So this continuous ESD and non-negative. It can be 0, but it can never be less than 0. So it is non-negative, true, and it is integrable, true. So C can be true, but let's check D. The ESD is always symmetric about origin. So the ESD can be symmetric, but there is no hard and fast bound that it has to be symmetric about origin, because so yeah, it is an even function, but it does not have to be symmetric about origin. So the true is option is C. The ESD is non-negative and integrable over all frequencies. Next, the PSD of a signal is known to be SXF. What is the PSD of the signal modulated by a carrier frequency, FC? So the PSD of a signal is known to be SXF. What is the PSD of a signal modulated by a carrier, FC? Now this is an interesting problem. So you have XT. Now what is the signal that is modulated by by a signal? It is modulated by a carrier frequency FC. Means it is multiplied by cos 2 pi FC. As simple as that. Now the PSD of this is PSD of this is SXF. Now what is the PSD? PSD is the Fourier transform of the autocorrelation. Now if we take this to be YT, then what is SYF? SYF is just Fourier transform of RY by F. Now what is RY by F? RY by F is the integration YT plus tau or T minus tau d tau over T over sorry dt over T tau over tau, sorry, over tau d tau, not T minus tau, tau minus tau. So y tau minus d tau over all tau. can just do x tau minus t cos 2 pi fc tau, and another is cos 2 pi fc tau minus t. Okay, so cos 2 pi fc tau minus t cos 2 pi fc tau minus t theta. Now this ultimately will lead to shifting by both. It will basically, if you take the cos function, the cos function has two spikes, one at fc and another at minus fc. So here in this product, the x power spectral density of x will be once shifted by this fc, and in another turn it will be shifted by minus fc. So your eventually your solution will be sxf equal to sxf minus fc plus sxf plus fc. Again, this is a very standard derivation you can find in the lecture or in any textbook. So it is the sum of the two frequency shifts. Our option C. Now null bandwidth of a signal is defined to be the least frequency such that SF naught equal to 0. So the first zero crossing frequency is the null bandwidth. Now we have to find the null bandwidth for rectangular T by T. So rectangular T by T means it is like this. Okay, so rectangular T by T means here minus T by 2 to T by T. have to find the ESD of this signal, and then you have to find the norm frequency. So the ESD of this signal, this is a rectangular function, so the ESD of this signal turns out to be sync, because it is the Fourier transform here. So it turns out to be sync, T sync pi f t. Now so it is T sync pi f t. Now we have to find where T is the first zero crossing point of T sync pi f t. So T sync pi f t means it is T sine pi f t by pi f t. Now at zero crossing or null bandwidth, this is your SF. So at null bandwidth, SF naught is equal to this thing, T sine pi f naught t by f pi f naught t is equal to 0. So ultimately, for this to be 0, this term has to be a multiple of pi. So pi f naught is equal to n pi, because whenever sine has n pi or multiple of pi in its argument, it will go to 0, and hence the power central density goes to 0. So f naught t will be equal to n, or f naught is equal to n by t. Now f naught is by definition the least frequency at which we have ESD equal to 0. So it is actually 1 by t, because 1 is the least one. So f naught is equal to 1 by t. The correct answer is 1 by t. Now xt is equal to sync pi t, capital T. Yt is the derivative. So find the ESD. Now to find derivative of Fourier transform, and from there we can square the Fourier transform with the ESD. Now to find the derivative of the Fourier transform, we have to use the differential property. So what does the differential property say? That it will get multiplied by the 2 pi f, 2 pi jf, by jf. So when you have sync pi xt is equal to sync pi small t capital T, its Fourier transform xn is sync, its Fourier transform is rectangular t by t 1 by t. Okay, so sorry, this is frequency. So it will be f t. This one is slightly wrong here. The Fourier transform of sin pi t is shown to be this, but it is still in time domain, as you can see. So it will not be in, this will not be t, this will be f, and this will not be by t, this will be multiplied by t. Okay. So it is actually t rectangular f t. Okay. Now the differentiation property states that the Fourier transform of dxt dt you will just multiply with 2 pi f, 2 pi jf. So it will be 2 pi jft rectangular ft. Now you whole square this to get the power spectral density of the derivative. So to get the power spectral density of the derivative, whole square this, which gives you minus 4 pi square f square t square rectangular square ft. So it is not here in this, you will disregard the negative of course, because the energy spectral intensity can actually, this will be mod square, so the mod on square, so you first take a mod and then square, so that's why there is no negative sign, so it will just be 4 pi square f square t square rectangular square. So 4 pi square f square t square by rectangular square. So this one is correct, but it will be 4 pi square f square t square. The option is written in a wrong way. Rectangular square f t. This is the answer, correct answer. It is of the form of d, but the capital T should be in the numerator, not in the denominator, because it is already multiplied by frequency. So it is, since it is already multiplied by frequency, if you divide it by time, so it becomes frequency square, which is dimensionally incorrect. To match the dimension, it should be f into t, so that it is dimensionless. So yeah, this concludes our first part, auto pollution and PSD. Next we will be focusing on another part, which is amplitude modulation. So I hope amplitude modulation has also been done in class. So in amplitude modulation, the carrier frequency is 1 megahertz and the modulating signal, that is the message signal, is 10 megahertz. So what is the frequency of the sidebands? So this is a very simple answer. So the, as you know, the frequencies get added. So if your carrier frequency is fc, so the frequency of the sidebands will be fc plus fm and fc minus fm. So 1 megahertz means 1000 kilohertz. So one will be 1000 plus 10, so 1010 kilohertz, and another will be 1000 minus 10, or 990 kilohertz. So it's either 990 kilohertz and 1010 kilohertz, or you can say 1.010 megahertz and 0.99 megahertz. So both option C and option B are correct actually. They're just different ways of writing the same thing. But the lower sideband is at 0.99 megahertz or 990 kilohertz. The upper sideband is at 1010 kilohertz or 1.01 megahertz. if the modulation index of an AM wave is increased from 0 to 1, the transmitter power P1 becomes, when the modulation index is 0, means there is no modulating signal, only carrier, pure carrier. So the power is P naught. So Pt is P naught in that case, with mu equal to 0. That is no modulation, pure carrier. So it is pure carrier. Now, second is because when the modulation index is 1, then the modulation index is 1, the power is. So the amplitude becomes mu AC. So plus mu plus AC. So this is the modulating amplitude. So this is the modulating amplitude. And it gets added with the carrier amplitude. So it is AC square by 2 plus mu square AC square by 2. And this one will be 1 by 2. This one will get multiplied by 1 by 2 because you only take one side back. So it becomes AC square by 2 is P naught. So and mu is 1. P naught plus P naught by 2. So it is 1.5 P naught. So P naught goes to 1.5 P naught. What is the modulation index in amplitude modulation? The ratio of carrier frequency to modulating frequency, the ratio of maximum frequency deviation to carrier frequency, ratio of peak amplitude of modulating signal to peak amplitude of carrier signal, ratio of bandwidth to the highest frequency component of the modulating signal. So here, of course, it's not frequency. Amplitude modulation is defined by its amplitude. So frequency bandwidth options are wrong. The only correct answer is option C. The ratio of the peak amplitude of modulating signal to the peak amplitude of the carrier signal. That is your correct answer. Okay. Now, output of an AM signal is this. Here you have to decompose this AM signal into carrier and message parts. So carrier, there is a carrier signal, there is a message signal, and then this message signal, carrier signal will not create one carrier component and two sidebands. So you have to isolate them, and from there you have to deduce the message signal frequency, the carrier signal frequency. So please attempt this. It's easy. So I'll give you 5 minutes. After 5 minutes, we will start solution. Yeah. Yeah, break. Break means basically I have given problem, so they will inevitably will be not able to solve it. Yeah, let's tackle this problem. So here we have to write this cos and sine term in terms of this signal. Now, as you can see, this cos 2000 pi t, this part is the center frequency. So without a doubt, this will be your carrier frequency. So these are your side bands, 2200 and 1800 are your side bands. So so here 4 cos 2000 pi t plus cos 1800 pi t plus cos 2200 pi t. Now this you can write as cos 2000 minus 200 pi t So this will be plus cos 2000 plus cos 2000 minus 200 pi t. Now cos a minus b and this is cos a plus b. So together they form 2 cos a cos b. So this will just become 2 cos 2000 pi t into cos 200 pi t. So this will just become 4 cos 2000 pi t. You take you take 2 cos 2000 pi t common. This 2 cos 2000 pi t. Rather, you take 4 cos 2000 pi t. You take the entire carrier as common. So you have 1 here, and you have half into cos 200 pi t. So now if we compare this with AC cos 2 pi fct into 1 plus mu AC cos mu AM cos 2000 pi t 200 pi t. So here we can see the FC is 2 pi FCT is basically 2000 pi. 2 pi FC is 2000 pi. So FC is 100, sorry 1000, and 2 pi FM is 2 pi FM is 200 pi. So FM is 100. So this is 1000 hertz carrier frequency and 100 hertz message frequency. So the correct answer is 1100. Now for the signal given in Q4, find the modulation index and amplitude of the carrier. Now what is the modulation index and carrier amplitude? So carrier amplitude is the carrier amplitude A is 4 and the modulation index is half. So by direct comparison we can say that the A is 4 and this is half, mu is half. Next, find the in the same signal, now find the sideband power. So sideband power means the power content in this part. Okay, so here this it is basically composed of mu into AC, the power in mu AC cos 200 pi, because mu AC cos 200 pi t is the amplitude of the sideband cos 2000 pi t. So this is one term, and another term is the pure carrier AC cos 2000 pi t. Now this part is the sideband. And what is the sideband amplitude? The sideband amplitude, A sideband, is mu AC cos 200 pi t. So what is the sideband power? It is simply mu square AC square. So the power of mu is mu, AC is AC, and this cos term is half. So mu square AC square by 2. Now we have derived mu to be half, so it is 1/4. AC square is 4, so 4 square by 2. So 1/4 is cancelled, 4 by 2, 2. So the sideband power is 2. none of the above. The sideband power is 2. Now, what is the power modulation power efficiency? So, modulation power efficiency is defined as efficiency of the modulation is defined as P sideband, because the sideband contains the message. So, we want the sideband to be the maximum of the as much as possible of the total power. So, total power P sideband by 2 P total power gives us the efficiency. So, total power is P sideband plus P carrier. So, here you have. Now, what is the sideband power? Sideband power we have derived to be 2, and the carrier power is 4 square by 2. So, and carrier amplitude is 4. So it is 2 by 16 by 2, 8, 8 plus 2, 10, 1 by 5. So the efficiency is 1 by 5. Here they are getting this to be 4. No, but the correct answer is not 4. This is again wrong here. So it is not 4. This one 8 is correct, but this is not 4. This is 2. So 2 by 2 plus 8. So it is 1 by 5. The correct answer is 1 over 5. Okay, this is the correct answer, 1 over 5. In AM, the modulation envelope has a peak value which is triple the unmodulated carrier. So the modulation envelope means the entire thing. So it has 2 powers. So one is AC square and another is mu square AC square by 2. And unmodulated carrier power is AC square by 2. So here we say, it is saying that the modulation envelope power, that is the sideband power plus carrier power. So AC square by 2 plus mu square AC square by 4. Okay, so I have made one mistake here. So this sideband power will be mu square AC square by 4. So no, mu square AC square by 4. So this will be 1. So if this is 1, okay, sideband power is 1, then the efficiency will be 1 by 1 plus. So 1 over 9. The efficiency will be 1 over 9. This is because the sideband power is 1. Okay. So if the correct answer is A, option 1 over 9. Not this. 1 over 9. And the sideband power is 1. Not this, but 1. Because, see, the sideband is mu AC cos 2 pi FMT and cos 2 pi FCT. So the total power will be, both of these sinusoids will contribute to the total power. So mu square AC square into half into half. So it is mu square AC square by 4. Okay. So it is 1 and 1 over 9. And here because the total power is this and the carrier power is c square by 2. So this is by the problem, this modulation envelope power is 3 times s square by 2. So mu square s square by 4 is equal to 2 into s square by 2. So this cancel, this cancel. So mu square is 4. So mu is coming to 2. So mu is coming to be 2. So mu 2 means it is over modulated. So correct answer is D. Now we will come to the next problem. Now let's come to question 9. Consider the system shown below. The modulating signal MT has a 0 mean and its maximum value is AM. It has bandwidth WM. So there is a signal which has a 0 mean and its maximum value is AM and its bandwidth is WM. The nonlinear device has an input-output characteristic as AXT plus BX squared T. So it is a square law device. Now the filter should be, what should be the filter? So we have to get the filter so that we get an AM signal. So we have to find the filter which will give us an AM signal. So we have a signal called MT. We have a signal called MT. Now MT gets multiplied with cos omega ct to give us xt. So xt is MT cos omega ct. Fine. So it gets multiplied with the carry. Now there is a square law device which gives us yt is equal to a xt plus b x squared t. So this is a mt cos omega ct plus b m squared t cos square omega ct. Now if this is yt, we have to find a filter so that we can get AM signal from this. So this one we can write as AMT cos omega ct plus bm squared t by 2 1 plus cos 2 omega ct. So it ultimately has three parts. One is bm squared t by 2, one is AMT cos omega ct, and one is bm squared t by 2 cos 2 omega ct. Now we want this part. We don't want this. We don't want this. So we need to design a BPF. We need to design a BPF because we have to filter out two terms, not one, but two terms. So option A and B can be easily eliminated. Now the choice is between option C and option D. Now we have to make the filter with the cutoff frequency such that this 2 times the value. So m squared t has to be negative. So mt has a bandwidth wm. So we have to go up to 2w. So one cutoff will be up to 2w. And another cutoff will be at, one cutoff is at f naught minus wm is greater than 2w. So f naught is minus wm is greater than 2w. So f naught is greater than 3w. So we ignore the 2wm part. The edge should be at 2wm. So the center will be at 3wm. And another is f naught minus 0.5 wm, but w should be greater cos 2 omega. To ignore this cos 2, cos 2 omega. So it will have both of them with option C. So with option C, it can filter out both of these terms. Here the diagram is given. You can follow this diagram to accurately understand why we will have a filter like this. Next, what is the modulation index? The modulation index will be determined by the output of the filter. So here you can see the output of the filter is 2BMT plus A cos omega ct. So you take A common, so it is 2B by A mt plus 1 cos omega ct. So the output of the filter is 2B by A into A. So 2B by A into A is the modulation index and the carrier amplitude is A. So this concludes our class. We have solved problems and these assignments will be uploaded in the course page. Follow there. If you have any doubts, please ask in the next class or this class itself if you want. So yeah, with that I will be concluding my class today. Thank you.